400,000 kilometers. That's how wide the X-ray halo around 3I Atlas stretches into space, a ghostly envelope of high-energy photons emanating from a frozen rock just a few kilometers across. XRISM captured it in late 2025 during a narrow observation window, when the object was literally hidden behind the sun from Earth's perspective. Here's what's keeping scientists up at night. Is this just an unusually gassy comet throwing a tantrum? Or did we just photograph our first alien spacecraft mid-flight? Stay with me, because the answer gets stranger the closer we look. You'll want to stay with us as XRISM continues tracking this visitor, and scientists refine their models. Subscribe and follow along, because each new observation brings us closer to understanding whether we're witnessing extraordinary comet physics or something far stranger. Now, let's settle in and unravel this interstellar mystery together. Picture this. You're trying to photograph a ghost. Not just any ghost, but one that's moving at thousands of kilometers per hour, hidden directly behind the brightest object in our sky. Wrapped in a cloud of ionized gas that stretches farther than the distance between Earth and the Moon. You have one shot, one narrow window, and if you miss it, the ghost vanishes back into the darkness between stars, never to return. On November 26th through 28th, 2025, that's exactly what happened. The Japanese X-ray telescope, XRISM, floating in Earth orbit with its soft X-ray instrument called X-TEND, captured something extraordinary. Something that has never been photographed before in the history of astronomy. The target was 3I Atlas, only the third confirmed interstellar object ever observed by humanity. And what XRISM saw should not exist according to everything we thought we knew about comets. The image shows an X-ray glow forming a halo roughly 400,000 kilometers in radius. Let me put that in perspective for you. The average distance between Earth and the Moon is 384,000 kilometers. This halo is bigger than that. We're talking about a structure so enormous that you could fit the Earth inside it more than 10 times over, with room to spare. And all of this is emanating from a tiny nucleus, a chunk of ice and rock just a few kilometers across. The scale difference is staggering, almost incomprehensible. It's like finding a grain of sand that's somehow generating a fog bank the size of a city. Now here's where things get interesting, and by interesting, I mean potentially world-changing. We have two possible explanations for what we're seeing, and they couldn't be more different. The first is the safe, scientific explanation. This is a natural comet with an extreme gas cloud interacting with the sun's solar wind in ways we've never observed before. Charged particles from the sun collide with neutral atoms boiling off the comet's surface. Electrons jump between atoms, and boom, you get X-rays. We've seen this process in solar system comets since the 1990s. Case closed, mystery solved, everyone goes home. But then there's the second explanation, the one that keeps astronomers up at night and makes SETI researchers lean forward in their chairs. What if this glow isn't natural at all? What if we're looking at evidence of magnetic shielding, a plasma trail from an engineered object, something that was designed and built and sent here from another star system? What if this isn't a comet, but a machine? I know what you're thinking. That sounds like science fiction. That sounds like the plot of a movie where humanity discovers alien life and everything changes forever. But here's the thing about science fiction. Sometimes it becomes science fact. And right now, we're sitting in that uncomfortable space between the two, staring at data that doesn't quite fit either narrative perfectly. Among only 3 known interstellar objects ever observed, 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I Atlas, this is the first to produce a confirmed X-ray detection. That's not just interesting, that's a milestone. It's like being the first person to hear radio waves from space, or the first to detect an exoplanet. It opens a door we didn't even know existed. If this glow is natural, if it's just an extraordinarily active comet behaving in ways that push the boundaries of comet science, then we need to rewrite our models. We need to understand how a relatively small object can generate such a massive, energetic envelope. The implications ripple outward. What else are we missing about these cosmic wanderers? What other surprises are waiting for us in the space between stars? But if it's artificial, if there's even a 1% chance that we're looking at technology, then we're not just rewriting models. We're rewriting history. We're confronting the reality that we are not alone, that intelligence exists elsewhere, and that it's capable of crossing the unimaginable distances between stars. That's not hyperbole. That's the actual stakes of this observation. Now, I'm going to be honest with you. I'm not here to sell you a definitive answer, because we don't have one yet. The data is fresh, literally just a few weeks old. Interpretations are being debated in real time by scientists around the world. What I'm here to do is walk you through both explanations, show you the evidence, point out where things don't add up, and let you see why this might be one of the most important astronomical observations of the 21st century. This isn't going to be a dry lecture full of jargon and equations. Think of this more as an investigation, a deep dive into a cosmic mystery that's unfolding right now. We're going to follow the data wherever it leads, even if it makes us uncomfortable. We're going to ask questions that sound absurd until you realize they might not be. And we're going to stay curious, because curiosity is the only tool we have when faced with something genuinely new. So let's start with the basics. How did we even get this image in the first place? Why was XRISM the only instrument that could capture it? And why did this observation almost not happen at all? The answers involve orbital mechanics, solar glare, and a technical feat that borders on the miraculous. Astronomy is often about being in the right place at the right time, with the right tools. But sometimes it's about overcoming impossible odds to see something that every other instrument on Earth and in space is completely blind to. That's the situation XRISM faced in late November 2025, when 3I Atlas was passing through solar conjunction, hidden directly behind the sun from Earth's perspective. Let me explain why this matters. When an object is behind the sun relative to Earth, you can't see it with optical telescopes. The sun's glare overwhelms everything. Infrared instruments struggle for the same reason. Radio telescopes might pick up something, but they're not ideal for studying small, fast-moving objects. For all practical purposes, 3I Atlas was invisible to humanity during those critical days in late November. It was there, speeding past us on its hyperbolic trajectory through the solar system, but we couldn't touch it with our usual tools. Enter XRISM, an X-ray telescope that doesn't care about visible light or solar glare. X-rays from the sun are a different story, but XRISM was designed to filter and process high-energy photons in ways that optical telescopes can't. So while ground-based observatories were helplessly staring at blank sky, XRISM quietly maneuvered itself into position and started collecting photons. The observation itself was a masterpiece of precision engineering. Over roughly 17 hours of exposure time, XRISM adjusted its attitude 14 times to keep 3I Atlas centered in its field of view as the object moved across the sky. Think about that for a moment. This isn't like pointing a telescope at a star that barely moves. This is tracking a small, dim target moving at interstellar velocities, hidden in solar glare, while maintaining the precise orientation needed to collect enough photons to form an image. One mistake, one drift in alignment, and the entire observation could have been ruined. The field of view covered by X10, XRISM's soft X-ray instrument, spans roughly 3 million kilometers across. That sounds enormous until you realize the X-ray halo itself stretches about 400,000 kilometers in radius. So we're not talking about a faint smudge barely visible at the edge of the detector. This is a substantial, significant feature, taking up a meaningful portion of the image. It's real structure, not just background noise or instrumental artifacts, though I'll get to why scientists are still being cautious about that interpretation. The preliminary spectrum extracted from the central region shows emission excesses that line up with what you'd expect from charge exchange processes involving carbon, nitrogen, and oxygen. When solar wind ions slam into neutral atoms from the comet's coma, electrons get captured, and the resulting atomic transitions emit X-rays at specific energies. The XRISM data shows peaks consistent with this mechanism. So far, so normal for a comet, right? Except the scale is all wrong. The brightness, the extent, the sheer volume of space that this halo occupies, all of it pushes against what we know about comets. To generate this much X-ray emission over such a large area, you'd need a truly massive gas cloud, far more extensive than anything we've seen from comets of similar size. Either 3I Atlas is outgassing at a rate that defies our models, or something else is going on that we haven't figured out yet. Now, before we get too excited, I need to mention the caveats. The published image comes from quick look processed data, meaning it hasn't gone through the full pipeline of calibrations and corrections that will happen over the coming months. XRISM scientists themselves note that instrumental effects like vignetting, where the sensitivity of the detector varies across the field of view, or detector noise could potentially mimic a diffuse halo. They're not saying the halo is fake, but they're being appropriately cautious about claiming a definitive detection before all the analysis is complete. Still, the fact that they released this image at all suggests they think it's real. Scientists don't usually publish preliminary results unless there's something genuinely interesting worth sharing, especially for a high-profile mission like XRISM, observing a high-profile target like an interstellar object. The orbital mechanics and timing made this observation window incredibly narrow. 3I Atlas is on a hyperbolic orbit, meaning it came from outside the solar system, swung past the sun once, and is now heading back out into interstellar space, never to return. Its inbound velocity was high, and its position relative to the sun during conjunction meant that XRISM had maybe a few days to capture this data before the geometry changed, and the opportunity was lost forever. Preparing for this observation was like trying to photograph a nearly invisible, fast-moving ghost behind a bright, blinding sun. The technical challenges were immense. The coordination required between mission planners, instrument operators, and data analysts was extraordinary, and yet they pulled it off. They got the image, and now we have to figure out what it means. What makes this even more remarkable is that no prior interstellar object had ever been imaged in X-rays. One I/Oumuamua passed through too quickly and at the wrong angle for X-ray observations. 2 I/Borisov was observed extensively, but never showed X-ray emission, or at least none that was detected. 3I Atlas is the first, which means we're literally breaking new ground here. We're opening up a new frontier in the study of objects from beyond our solar system. So we have this image, we have this halo, we have preliminary spectroscopy suggesting charge exchange. But does the rest of what we know about 3I Atlas support this interpretation, or does it raise more questions than it answers? Before XRISM captured that X-ray halo, 3I Atlas was already earning a reputation as one of the weirdest objects astronomers had ever studied. It wasn't just that it came from another star system, though that alone puts it in an incredibly exclusive club. It was the way it behaved, the way its composition defied easy categorization, the way every new observation seemed to add another layer of strangeness to an already bizarre object. Let's start with the basics. 3I Atlas is only the third confirmed interstellar object ever observed by humanity. 1 I/Oumuamua arrived in 2017 and immediately sparked controversy with its elongated shape, unusual acceleration, and lack of visible coma. Scientists debated whether it was a comet, an asteroid, or something else entirely, and that debate continues to this day. 2I/Borisov showed up in 2019 and was much more cooperative, behaving like a fairly normal comet with a coma, a tail, and all the expected features. 3I Atlas falls somewhere between those two extremes, displaying comet-like activity, but with enough oddities to make astronomers scratch their heads. The Hubble Space Telescope observed 3I Atlas in August 2025 and constrained the nucleus diameter to somewhere between 440 meters and 5.6 kilometers. That's a wide range, which tells you something about how difficult it is to pin down the exact size of a small, distant object surrounded by gas and dust. But even taking the upper estimate, we're talking about something relatively small compared to the X-ray halo it allegedly produced. A 5-kilometer nucleus generating a 400,000-kilometer halo is a ratio that should make any physicist pause. Ground-based and space-based telescopes in optical, ultraviolet, and infrared wavelengths all reported a coma of gas and dust, a dust plume, and hints of a tail. This is classic comet behavior. When a comet approaches the sun, solar radiation heats its surface, ice sublimates into gas, and that gas drags dust particles along with it, creating a visible cloud. So far, nothing unusual. But then you look closer at the composition, and things start to get weird. Near-infrared and optical spectroscopy from Gemini South and the NASA Infrared Telescope facility in July 2025 revealed abundant water ice grains in the coma. The spectral signature matched a mix of stony material similar to the Tagish Lake meteorite and ice. Tagish Lake is a carbonaceous chondrite, a primitive meteorite rich in organic compounds and minerals that formed in the early solar system. Finding similar material in an interstellar object suggests that planet formation processes might be similar across different star systems, which is actually kind of reassuring. It means the laws of physics work the same way everywhere. Then the James Webb Space Telescope took a look in August 2025 and found something that wasn't reassuring at all. The coma was dominated by carbon dioxide, along with water, carbon monoxide, carbonyl sulfide, water ice, and dust. Now, finding these molecules isn't surprising. Comets are dirty snowballs full of volatile compounds. What was surprising was the ratio. The carbon dioxide to water ratio was approximately 8:1, far above typical solar system comet norms. Most comets we've studied have much more water than carbon dioxide. This ratio was off the charts. Why does that matter? Because it tells us something about where 3I Atlas formed and what conditions were like in its home star system. A high carbon dioxide to water ratio suggests formation in a very cold environment, possibly in the outer regions of a protoplanetary disk where carbon dioxide ice is stable, but water ice might be less abundant. Or it could indicate a different composition in the parent molecular cloud. Either way, it's not what we typically see, and it adds another data point to the growing pile of evidence that this object is genuinely alien in more ways than one. The UV observations from the Neil Gehrels Swift Observatory added yet another layer of strangeness. They detected hydroxyl emission at a heliocentric distance of about 3.5 astronomical units. For reference, 1 astronomical unit is the distance from Earth to the Sun. So 3.5 AU is out past Mars, approaching the orbit of Jupiter. At that distance, sunlight is much weaker, and you wouldn't expect water ice to sublimate efficiently. Most comets become inactive that far from the Sun. But 3I Atlas was pumping out hydroxyl, which forms when water molecules break apart under UV radiation, at a rate of approximately 1.35 times 10 to the 27th molecules per second. That translates to about 40 kilograms per second of water being released into space. 40 kilograms per second, from a nucleus that might only be a few kilometers across, at a distance where water sublimation should be inefficient. That implies either a huge active surface area on the nucleus, meaning a significant fraction of its surface is exposed ice actively venting gas, or there's an extended source, perhaps icy grains in the coma, that are slowly sublimating and contributing to the overall gas production. Neither scenario fits neatly into our standard comet models. And then there's the polarimetry. Recent polarimetric observations covering phase angles from 7.7 degrees to 22.4 degrees showed that 3I Atlas exhibits a deep, narrow, negative polarization branch, approximately negative 2.7% at 7 degrees, with an inversion angle around 17 degrees. If that sounds like technical jargon, let me translate. When you measure how light is polarized after reflecting off an object, you can learn about the size, shape, and composition of particles in its atmosphere or on its surface. The polarization behavior of 3I Atlas is unprecedented among known asteroids and comets. Nothing we've studied before behaves like this. It suggests surface or coma properties, unlike anything in our existing catalog. So let's take stock. Before XRISM ever captured that X-ray halo, we already knew that 3I Atlas was a volatile-rich object with unusual composition, active outgassing at large distances, and polarization properties that don't match any known comet or asteroid. It was already strange. The X-ray detection didn't come out of nowhere. It's one more piece of a puzzle that doesn't quite fit together. One more data point in a growing collection of anomalies. And that raises an uncomfortable question. Are we trying to force this object into categories that don't apply? Maybe 3I Atlas represents a new class of interstellar object, something our taxonomy wasn't designed to handle. Or maybe, just maybe, it's not a natural object at all. Let's return to the core anomaly, the thing that started this whole investigation. A relatively small nucleus, no more than 5.6 kilometers across, generating an X-ray halo roughly 400,000 kilometers in radius. That's not just big. That's orders of magnitude larger than what you'd expect from an object of this size. And when something in nature is orders of magnitude off from your predictions, it means either your model is wrong, your measurement is wrong, or something genuinely unexpected is happening. The standard model for cometary X-rays has been around since the 1990s, and it's pretty well established. It works like this. The sun constantly emits a stream of charged particles called the solar wind. These particles, mostly protons and heavier ions, travel outward through the solar system at hundreds of kilometers per second. When they encounter a comet, they slam into neutral atoms in the comet's coma, things like carbon, oxygen, nitrogen. The solar wind ions are highly charged, meaning they're missing electrons. When they collide with neutral atoms, they can capture electrons in a process called charge exchange. This leaves the ion in an excited state, and when it relaxes back to its ground state, it emits an X-ray photon. This process has been observed and documented in dozens of solar system comets. It's not controversial. It's textbook physics. And the XRISM spectrum shows emission excesses that match exactly what you'd expect from charge exchange involving carbon, nitrogen, and oxygen species. So on one level, everything checks out. We know the mechanism, we see the signature. Problem solved, except for the scale. For a halo of that size and brightness, you need a truly massive coma. Let's do some rough math here. The halo has a radius of 400,000 kilometers, so its volume is on the order of 10 to the 17 cubic kilometers. Even if the gas density is extremely low, which it probably is, you're still talking about a huge total mass of gas spread out over that volume. And this gas has to be replenished continuously because the solar wind is constantly blowing it away. So the nucleus has to be outgassing at a rate high enough to maintain this enormous cloud. Now, we know from the UV observations that 3I Atlas was producing water at about 40 kilograms per second at 3.5 AU. That's substantial, but is it enough to explain a 400,000 kilometer halo? And what about the carbon, nitrogen, and oxygen that are actually generating the X-rays? How much of those gases are being released? We don't have precise measurements, but based on typical comet compositions, you'd expect comparable or higher rates for carbon dioxide and carbon monoxide, which were detected in abundance by JWST. Even being generous with these numbers, you start running into problems. How much mass does the nucleus have to lose to sustain this cloud? Given the size constraints from Hubble, is there enough volatile material in the nucleus to maintain this level of outgassing? How long can it keep this up? These aren't trivial questions. Comets have finite lifetimes. They run out of gas. And if 3I Atlas is burning through its volatiles at an extraordinary rate to produce this halo, it should be much brighter and more active than what we observe in other wavelengths. Then there's the instrumental uncertainty to consider. XRISM scientists have been careful to note that the halo might be an artifact caused by vignetting or detector noise rather than a real diffuse cloud. Vignetting means the detector is more sensitive in the center than at the edges, so a point source could appear to have a faint extended glow just because of how the instrument responds. Detector noise could create a similar effect, making empty space look like it has a faint signal. The data came from quick look processing, which means the full calibration pipeline hasn't been applied yet. Over the coming months, as the XRISM team works through the data more carefully, they'll be able to determine whether the halo is real or instrumental. If it's instrumental, then this whole mystery evaporates, and we're back to 3I Atlas being just a weird comet with no X-ray halo. But if it's real, if the halo survives the full analysis, then we have a genuine puzzle on our hands. There are some creative ways to stretch the standard model without breaking physics entirely. Maybe 3I Atlas has an extended coma composed of large icy grains, as suggested by the spectroscopy. These grains could slowly release gas as they travel outward, spreading the source of neutral atoms over a vast region. That would dilute the density, but increase the volume, allowing a faint X-ray glow to appear over hundreds of thousands of kilometers. It's not the typical way comets work, but it's not impossible either. Another possibility is that the coma is highly asymmetric, concentrated in certain directions due to non-uniform outgassing or the solar-wind interaction. If the X-ray emission is stronger in specific regions, and the image we're seeing is a projection of that three-dimensional structure, it could appear more extended than it actually is. Again, not standard, but plausible. The bottom line is that we don't yet have enough information to make a definitive call. We don't know the gas density distribution in the coma. We don't know the exact composition at the distances where the X-rays are being generated. We don't have a detailed spatial map of the halo to see if it's uniform or patchy. All of these uncertainties leave room for both natural and extraordinary explanations. What we can say is this: the standard model offers a plausible mechanism, charge exchange, that matches the spectroscopic signature. But the scale and intensity of the halo push that model to its limits, maybe beyond. It requires conditions that are extreme by comet standards, though not necessarily impossible. Further data and more sophisticated modeling will be needed before we can conclude anything with confidence. But what if the natural explanation is wrong? What if we're trying to fit a square peg into a round hole, forcing an artificial object into a cometary framework because that's the only framework we have? Let's explore that possibility, not because it's likely, but because the implications are too important to ignore. All right, let's venture into territory that makes most scientists uncomfortable. Let's ask the question that sounds like science fiction, but might not be. What if 3I Atlas isn't a comet at all? What if it's something engineered, designed, built by an intelligence that isn't human? What if we're looking at the first confirmed image of an alien probe, and we almost missed it because we assumed it was just a chunk of ice? I'm not saying this is what's happening. I'm saying it's a hypothesis worth exploring, because the data we have doesn't quite fit the natural explanation as neatly as we'd like. and because the stakes are so high that we can't afford to dismiss possibilities just because they sound unlikely. Let me lay out 3 speculative scenarios, each of which could explain the X-ray halo without invoking standard cometary processes. First scenario, magnetic shield or plasma sail. Imagine an object surrounded by a large magnetized field or a bubble of plasma. This field deflects the solar wind, creating a bow shock where the charged particles pile up and interact. At the boundary of this magnetic shield, you'd get charge exchange happening on a massive scale, producing X-ray emission. The halo wouldn't be a gas cloud from sublimating ice. It would be the signature of a protective field, something designed to shield the object from radiation and particle impacts during its journey through interstellar space. Think about Earth's magnetosphere. Our planet's magnetic field extends tens of thousands of kilometers into space, deflecting solar wind and protecting us from harmful radiation. When the solar wind interacts with the magnetosphere, you get auroras and other energetic phenomena. Now scale that down to an object a few kilometers across, but with an artificially generated magnetic field, strong enough to create a similar effect. The X-ray halo would be the visible signature of that field, interacting with the solar environment. Second scenario, plasma exhaust or propulsion trail. What if 3I Atlas is actively decelerating, shedding velocity as it passes through the inner solar system? If it's using some form of ion drive or plasma propulsion, it could be ejecting ionized particles behind it. These particles would form a trail, and when they interact with the solar wind, they'd emit X-rays. The halo wouldn't be symmetric around the object. It would be concentrated in the direction of travel, marking the path of expelled propellant. We've seen this kind of thinking before with 1I/Oumuamua, which showed a non-gravitational acceleration that some scientists proposed could be explained by outgassing, while others suggested more exotic mechanisms. With 3I Atlas, we're not seeing obvious acceleration anomalies yet, but if the X-ray halo is related to propulsion, it might be a subtler effect, something that only shows up in high-energy observations. Third scenario, deliberate release of material. Maybe the object vented gas or ionized material intentionally, not as a byproduct of comet-like sublimation, but as a purposeful action. This could serve multiple functions: radiation shielding, thermal management, course correction, or even communication. The release would create a large gas or plasma cloud that interacts with the solar wind, producing the observed X-ray emission. The timing, shortly before or during solar conjunction, could be significant. Maybe the object was using the sun's gravity for a slingshot maneuver and needed to manage heat or adjust its trajectory. Now, why would anyone entertain these wild ideas? What evidence beyond the X-ray halo supports them? Well, there's the unusual carbon dioxide to water ratio, far higher than typical comets. If 3I Atlas is artificial, its composition might reflect the materials used in its construction rather than natural accretion processes. There's the high volatile activity at large distances, suggesting either unusual thermal properties or an internal heat source. There's the unprecedented polarimetric behavior, which could indicate artificial surface materials or coatings. And then there's the simple fact that an interstellar object exhibiting such extreme behavior challenges our entire taxonomy. We have categories for asteroids and comets, but maybe those categories are parochial, limited to our own solar system. Maybe interstellar objects form a distinct class, and some members of that class are technological artifacts. Before you dismiss this as fantasy, consider that serious scientists have proposed similar ideas for other interstellar visitors. Avi Loeb at Harvard has been vocal about the possibility that 1I/Oumuamua could be artificial, and while his ideas are controversial, they're grounded in legitimate physics. The fact that such hypotheses can be discussed openly, even debated, shows that the scientific community is at least willing to consider extraordinary explanations when the data is sufficiently strange. But, and this is crucial, Extraordinary claims require extraordinary evidence. Right now, we don't have that. We have ambiguous data that can be explained, albeit imperfectly, by natural processes. The X-ray halo, the compositional oddities, the polarimetry, all of it could be natural phenomena pushed to their extremes. Comets are complex objects, and interstellar comets are even less understood. It's entirely possible that 3I Atlas is just showing us how little we actually know about these visitors. What we need to settle the question are more observations. Detailed X-ray light curves showing how the halo evolves over time. Spatial mapping of the halo's density distribution to see if it's symmetric or directional. X-ray polarimetry to determine if the emission has any preferred orientation. Radio observations to search for plasma or charged particle signatures. Multi-wavelength monitoring as the object moves away from the sun. Without those additional data points, we're stuck in the realm of speculation. Human-made, or rather alien-made craft remains an intriguing but unproven hypothesis. It's fun to think about, provocative to discuss, but not something we can conclude based on what we have now. Still, the implications are worth pondering. If 3I Atlas were artificial, what would that mean? It would mean that interstellar travel is possible, not just theoretically, but practically. It would mean another civilization achieved what we haven't, building machines capable of crossing light years. It would mean we're not alone, and more importantly, we're not the first. That changes everything. Our understanding of biology, intelligence, technology, and our place in the cosmos. But even if it's natural, even if it's just an unusually active comet from another star, that's still profound. It means the diversity of objects in the universe is far greater than we imagined. It means interstellar space is full of wanderers carrying the chemical signatures of distant worlds. And it means that every time one of these visitors passes through our neighborhood, we have a chance to learn something fundamentally new about how planets form, how life might arise, and what else is out there. So where does that leave us? With an object that defies easy categorization, data that raises more questions than answers, and a growing sense that we're on the edge of something important. Let's zoom out now and look at the bigger picture. How does XRISM fit into the modern era of X-ray astronomy? And what might this detection mean for future discoveries? Every so often, astronomy undergoes a revolution. Not the slow, steady accumulation of knowledge, but a sudden leap forward when new instruments open up previously invisible parts of the universe. Galileo's telescope revealed moons orbiting Jupiter. Radio astronomy discovered pulsars and the cosmic microwave background. The Hubble Space Telescope showed us galaxies forming in the early universe. Now, missions like XRISM are doing the same for high-energy astrophysics, revealing phenomena that optical telescopes simply cannot see. XRISM, launched by the Japan Aerospace Exploration Agency, was designed to capture high-resolution X-ray images and spectra of some of the most energetic processes in the cosmos. Supernova remnants, where massive stars died in cataclysmic explosions. Galaxy clusters, where hot gas glows at millions of degrees. The interstellar medium, the thin gas between stars where X-rays trace shocks and turbulent flows. These are the targets XRISM was built to study, and it's doing that brilliantly. But 3I Atlas? That wasn't on anyone's bingo card. Comets, even interstellar ones, were considered niche targets for X-ray telescopes. Sure, a few solar system comets had been observed in X-rays before, but they were never a priority. The fact that XRISM pointed at 3I Atlas and discovered this enormous halo is, in some ways, accidental genius. It shows the value of exploratory observations, of taking risks on targets that might not pan out, but could reveal something completely unexpected. What makes XRISM particularly well-suited for this kind of discovery is its sensitivity to diffuse X-ray emission. Many X-ray telescopes are optimized for point sources, like black holes or neutron stars, where all the emission comes from a tiny region. XRISM, with its wide field of view covering millions of kilometers at comet distances, can detect faint, extended structures that other instruments would miss. That's why the 400,000-kilometer halo showed up so clearly. It's exactly the kind of feature XRISM was built to find, even if nobody expected to find it around a comet. This opens up a new observational window. If 3i Atlas can produce an X-ray halo, what about other interstellar objects? What about solar system comets that we thought we understood? Should we be re-observing them with X-ray instruments to see if we missed similar features? The answer is probably yes. Astronomy is full of examples where old targets, revisited with new tools, reveal surprising secrets. Consider the broader context of XRISM's mission. It's reshaping how we see the energetic universe. Supernova remnants, once static shells in optical images, are now revealed as complex, turbulent structures in X-rays, with temperatures, densities, and velocities that tell us about the explosion dynamics. Galaxy clusters, previously just collections of galaxies, are now understood as vast reservoirs of hot gas, the majority of the cluster's baryonic matter, glowing brilliantly in X-rays. The interstellar medium, invisible in optical light, is mapped in exquisite detail through its X-ray emission, showing how energy and matter flow through the galaxy. And now, with 3i Atlas, we're adding comets and interstellar objects to that list. High-energy signatures, plasma interactions, phenomena that were completely invisible until now. This might mark the beginning of a new class of observations, where interstellar visitors are characterized not just by their optical appearance or chemical composition, but by how they interact with the solar environment in X-rays and other high-energy bands. Imagine future missions equipped with even more sensitive X-ray detectors, faster readout times, and better spatial resolution. Imagine being able to map the X-ray halo of an interstellar object in 3 dimensions, tracking how it evolves as the object moves through different regions of the solar system. Imagine combining that with radio observations of plasma, infrared mapping of dust, and UV spectroscopy of gas. The complete picture would be transformative. This also has implications for comet science in general. If 3i Atlas's halo is real and natural, it means comets, especially interstellar ones, can carry far more volatiles and generate far more extensive plasma interactions than we previously thought. That changes how we model comet formation, how we think about the delivery of water and organic compounds to planets, and how we assess the role of comets in the chemical evolution of planetary systems. It might also prompt us to revisit past data. Were there X-ray sources in old survey data that we dismissed as noise or background, which might actually have been interstellar objects passing through? Could some unexplained transient X-ray events be explained by comets or asteroids we didn't know were there? The detective work required to answer these questions will keep astronomers busy for years. And it's not just comets. What if other small bodies, asteroids, or Kuiper belt objects have properties that make them interesting X-ray sources under certain conditions? What if some near-Earth asteroids, when they pass close to the Sun, produce faint X-ray emission that we never thought to look for? XRISM has shown us that the universe is full of surprises, even in seemingly mundane targets like comets. The narrative arc here is clear. From Earth-based optical discoveries that first spotted 3i Atlas, to ground telescopes characterizing its orbit and coma, to space telescopes like Hubble and JWST revealing its composition, to Mars orbiters potentially observing it from a different vantage point, and finally to XRISM capturing it in X-rays. This is multi-wavelength, multi-platform astronomy at its best. Every instrument adds a piece to the puzzle, and the puzzle is only solvable when you combine all the pieces. Looking forward, there will be more observations of 3i Atlas as it moves away from the Sun and back into the darkness of interstellar space. XRISM might try to reobserve it if the geometry permits. Other telescopes will continue monitoring it as long as it's bright enough. The data will be reprocessed, refined, debated. Models will be built, tested, and revised. And eventually, we'll have a clearer picture of what this object is and what its X-ray halo means. But even if the mystery is solved, even if we figure out exactly what's going on, the fact that this detection happened at all is significant. It shows that XRISM is capable of discovering things nobody predicted. It shows that interstellar objects are more diverse and complex than we thought. And it shows that we're living in an era where the tools exist to study the cosmos in ways that were impossible just a few decades ago. So what comes next? More data, more analysis, more speculation. And beyond 3i Atlas, there are bigger mysteries waiting, deeper questions about the universe that we're only beginning to ask. Let's zoom out one more time and consider the broader cosmic context, the unknowns that still dwarf even this extraordinary discovery. While 3i Atlas might dominate headlines for a few weeks or months, it's important to remember that this is just one data point in a universe full of unsolved mysteries. Astronomy is a humbling field. Every answer we find opens up 10 new questions. Every discovery reminds us how much we still don't know. And the things we don't know, the genuine unknowns, far outweigh the things we've figured out. Take dark matter, for instance. We know it exists because we can see its gravitational effects on galaxies and galaxy clusters. We can measure how much of it there is, roughly 85% of all matter in the universe. But we have no idea what it's made of. Decades of experiments, including recent efforts like the LWEX Zeppelin experiment in 2025, have searched for dark matter particles and come up empty. We've ruled out large swaths of parameter space, but the mystery remains. Whatever dark matter is, it's still hiding from us. Or consider neutrinos, ghostly particles that barely interact with anything. Trillions of them pass through your body every second, mostly from the sun, and you never notice. We've detected neutrinos from supernovae, from the sun, from cosmic rays smashing into Earth's atmosphere, and even from distant astrophysical sources. But there are still fundamental questions about their masses, their mixing, and whether they play a role in larger cosmic structures. Every neutrino observation tells us something new, but the full picture is still incomplete. Fast radio bursts, brief flashes of radio emission from across the universe, were only discovered in the 2000s, and we're still not entirely sure what causes them. Pulsars? Magnetars? Colliding neutron stars? Alien transmitters? Okay, probably not that last one, but the point is, we don't know. Every new FRB detection adds data, but the theoretical models are still catching up. Exoplanet atmospheres are another frontier. We've found thousands of planets orbiting other stars, and we're starting to characterize their atmospheres using transit spectroscopy. We've detected water vapor, methane, carbon dioxide, even hints of more exotic molecules. But we haven't yet found a clear biosignature, an unambiguous chemical marker of life. That's the holy grail of exoplanet science, and it might be just a few years away, or decades depending on how lucky we get, and how good our instruments become. The reason I'm bringing up all these examples is to put 3i Atlas in perspective. Yes, the X-ray halo is strange. Yes, it's exciting. Yes, it might be one of the most important observations of the 21st century if it turns out to be artificial. But it's also just one thread in a much larger tapestry of cosmic mysteries. And the way we approach 3i Atlas, with multi-wavelength observations, careful analysis, and open-minded speculation, is the same way we approach all these other unknowns. This is the power of multi-wavelength, multi-instrument astronomy. Combining X-ray data from XRISM with optical and infrared from Hubble and JWST, ultraviolet from SWIFT, and potentially MAVEN, radio from ALMA or other arrays, gives us a complete picture that no single instrument could provide. It's like having multiple witnesses to an event, each seeing it from a different angle. The more perspectives you have, the closer you get to the truth. Looking forward, there are several big open questions about 3I Atlas and interstellar objects in general. First, are there more objects like this out there? How common are interstellar visitors that show high-energy halos? If 3I Atlas is unique, that's interesting in one way. If it's typical, that's interesting in a completely different way. We won't know until we detect more of them. Second, could some past unexplained phenomena be attributed to interstellar objects we didn't recognize? There are databases full of transient X-ray sources, brief flashes of high-energy radiation that appeared and disappeared without clear explanation. Some of those might have been interstellar comets passing through, invisible in optical wavelengths, but briefly lighting up in X-rays. Going back through archival data with fresh eyes could yield surprises. Third, what if some interstellar visitors are artificial? This is the big one, the question that makes people uncomfortable but can't be ignored. If there are engineered objects, probes, ships, or even debris from aliens, civilizations passing through our solar system, how would we recognize them? What signatures would they leave? And how many might we have missed because we weren't looking in the right way or at the right wavelengths? To settle the mystery of 3I Atlas specifically, we need more observations. Deeper X-ray exposures to confirm the halo and map its structure. Radio observations to search for plasma emission or other electromagnetic signatures. Polarimetric studies across multiple wavelengths to understand the scattering properties of the coma or whatever is producing the glow. Long-term monitoring to see how the halo evolves as the object recedes from the sun and the solar-wind interaction weakens. Each of these observations will narrow the range of possible explanations. If the halo fades in a way consistent with decreasing gas production, that supports the natural comet model. If it maintains its brightness or shows unexpected variations, that raises more questions. If radio observations detect structured plasma or unusual emission patterns, that could point towards something more exotic. There are also philosophical and societal implications worth considering, even if the chances are slim that 3I Atlas is artificial. If it turned out to be a probe, what would that mean for humanity? It would mean we're not alone, which is monumental. It would mean interstellar travel is achievable, which changes how we think about our future. It would mean there's a civilization out there capable of engineering on scales we can barely imagine, which is both inspiring and humbling. It would also reshape our priorities. Suddenly, planetary defense, the effort to detect and deflect dangerous asteroids, takes on new urgency. SETI, the search for extraterrestrial intelligence, gets more funding and more attention. Space exploration becomes not just a scientific endeavor, but a way to find neighbors. And the questions we ask shift from, are we alone, to, how do we make contact, and what do we say? But even if 3I Atlas is natural, even if every interstellar object we ever find turns out to be just a comet or asteroid, that's still profound. It tells us that the space between stars isn't empty. It's full of wanderers, debris from planetary systems that formed billions of years ago, messengers carrying chemical signatures from places we'll never visit. Every interstellar object is a time capsule, a sample of a distant world delivered to our doorstep, and we're only just beginning to learn how to read them. The real takeaway from all of this is humility and wonder. We don't know as much as we think we do. The universe is stranger, more complex, more surprising than our models predict. Every new data point, every unexpected observation is a gift because it challenges us to think harder, to be more creative, to consider possibilities we hadn't imagined. 3I Atlas is one of those gifts. Whether it's a comet pushing the boundaries of what comets can be, or something else entirely, it's forcing us to ask new questions. And questions are, where progress begins. Not answers, questions. The moment you think you have all the answers is the moment you stop learning. So here we are, in December 2025, staring at an image of a 400,000 kilometer X-ray halo around a small, fast-moving object from another star system. We have theories, speculations, hopes, and doubts. We have data that's tantalizing but incomplete. And we have a choice. We can dismiss it as just another weird comet, or we can lean into the mystery and see where it takes us. I know which option I prefer, because the history of science is full of moments where people dismissed the strange and unusual, only to realize later that they were looking at something revolutionary. Galileo's moons, pulsars, exoplanets, gravitational waves, all of them were met with skepticism at first, and all of them changed how we see the universe. Maybe 3i Atlas is the next chapter in that story. Maybe it's just a footnote. Either way, it's a reminder that we live in an age of discovery where the tools exist to see things our ancestors couldn't even dream of. And as long as we keep looking, keep questioning, keep pushing the boundaries of what's possible, we'll keep finding wonders that make us reconsider everything we thought we knew. So the mystery remains. The halo glows. And somewhere out there, beyond the edge of our solar system, 3i Atlas is speeding back into the darkness, carrying its secrets with it. We got one glimpse, one image, one chance to see something that might never pass our way again. What we do with that glimpse, what we learn from it, and what questions it inspires, that's up to us. The universe is full of ghosts, waiting to be seen. And we've only just started learning how to look.